for the invitation. Thank you for the invitation and introducing me. So I want to tell you today about a novel class of gadolinium-based contrast agent. This is a part of my PhD thesis. So let's start. So although magnetic resonance imaging, so MRI, is an advanced method which provides more accurate images than other methods, sometimes it is necessary to use contrast agent to have a better contrast, to have a better image. So contrast agents provide contrast enhancement in areas of application by interacting with water molecules nearby in tissue. But today I would like to focus on the paramagnetic group of the contrast agent, especially gadolinium-based contrast agent. So maybe you know gadolinium is an element of the lanthanide group, and it has a great paramagnetic properties thanks to the 7 unpaired electron. Unfortunately, gadolinium itself is very toxic. That's why it should be administered to our body as a, for example, chelate. So the first gadolinium-based contrast agent was investigated in May 1988, and since then contrast agent became very popular in magnetic resonance imaging. The first gadolinium-based contrast agent called Mickiewicz, and here you have the Mickiewicz, and Mickiewicz, it's a kind of a linear ionic contrast agent, and its molecular weight is about 500 grams per mole. And since this 1988, many scientists from all around the world made a huge progress in presenting new approaches with improving our gadolinium-based contrast agent, with improving safety, efficiency, efficacy, but also with reducing release of free form of gadolinium ions in our body. And regarding to the clinical practice over past 4 decades, here you have commonly used a very popular contrast agent in the hospital, using in the hospital. So we can divide them based on the structure, into the cyclic and linear, and based on the total charge into ionic and non-ionic. So current challenge is to create contrast agents which are fully biocompatible. So do not release toxic gadolinium ions or are gadolinium free. And one of these promising approach is to create lipid nanocarriers. And lipid nanocarriers include very popular solid lipid nanoparticles, but also liposomes. But lyotropic liquid crystalline nanoparticles are distinguished. So this structure exhibit long-range ordering, including bicontinuous cubic phase and also inverted hexagonal phase, bicontinuous cubic phase forming cubosomes, and this inverted hexagonal phase forming hexosomes. So these kind of structures, cubosomes and hexosomes, belong to the group of the isosomes because of their ability to self-organizing. And their stability depend on many parameters like pressure, temperature, but also structure and so on. And the other approach is to create contrast agent which exhibit high relaxivity. And in this case, in the opposite to the low molecular weight, very well known, very popular Mickiewicz, we propose in our system high molecular weight gadolinium chelating lipid, DTPA-BSA-Gd. And thanks to that, thanks to using this high molecular weight gadolinium chelating lipids, we can improve some dynamic parameter, molecular dynamic parameter, like reducing the molecular reorientation, extending reorientational correlation time, but also reducing this required amount of gadolinium to enhance the relaxivity. So I made an effort to create a novel class of gadolinium contrast agent. At least I tried, and I used 3 compounds. First one was glycerol monooleate, which was the matrix. Also gadolinium chelating lipids, so GD, DTPA, BSA, And the third one was pluronic, which was the stabilizer. And thanks to the dynamic light scattering, I measured the size of these samples. But first of all, I divided my samples into 3 groups. The first group is our unmodified system. Second one, this with low concentration of gadolinium, and a third one, this with high concentration of gadolinium. And as you can see, for every system, the average size is about 170 nanometers. Polydispersity index is always below 0.3, which means that we have a medium range polydispersity, which is good. And in every case, we always have negative zeta potential, negative charge. I did also the biocompatibility test because, as I mentioned, biocompatibility is very important for us. And for this purpose, I used 2 cell lines. First one, HeLa, which is a cancer cell line, and also MSAU 1.1, which is a normal cell line. And as you can see, they are fully biocompatible, so that's good for us. Relaxometry. So I measured longitudinal relaxation time for my samples, as well as longitudinal relaxation rate, because this is the inverse of the T1. And by knowing concentration of gadolinium in our samples, we could obtain from the slope the parameter called relaxivity. And relaxivity, in simple words, tells us how strong and how good our contrast agent is. Because the bigger number we have, the better for us. So in the first group, as you can see, we have the low concentration of DTPA and various concentration of pluronic. And in this case, the best results we have for the sample 1, so this with the lowest concentration of pluronic. The second part, so we have here the high concentration of DTPA, and but various, and constant concentration of pluronic. And here the best results we have for the first sample, so this with the highest concentration of gadolinium. And for the last group, we have a constant value of DTPA, but in high concentration, and a various number of pluronic, and the best result we have for the sample with the lowest concentration of pluronic. Here you have the results from every sample, and as you can see, the relaxivity, so this parameter which I mentioned is one of the most important, in every case is better and higher than commercially used contrast agent in the hospital, like Mickiewicz, Gadovis, and Dotarum, which is very good, of course, for us. So we wanted also to see how it's working in the MRI. So we did the magnetic resonance imaging, especially T1 weighted images, and we did it for the samples with the highest concentration of gadolinium. And as you can see, when we increasing the concentration of gadolinium in our samples, the brighter image we have. Which is good. That's why we can name it positive contrast agent, because they are brightening our image, and what is also important for us, that in the lowest concentration of gadolinium here, we have a better contrast than just for the sample of water. So yeah, it's working. It's very good. So we used also cryogenic transmission electron microscopy, because it's very important what is inside our samples. So as you can see, for these samples with this unmodified system, let's say, and this with low concentration of gadolinium, we can observe highly ordered periodic internal structure like cubosomes or hexosomes, but we also can observe the other self-assembled system like liposomes and so on. But what is important here, in the opposite to these samples with the high concentration of DTPA, because in these samples with higher concentration of DTPA, we can observe highly disordered interiors, so in vesicle-like shell. So we can suppose that incorporating our gadolinium chelating lipids into GMO lipid bilayer disturb this self-assembled lipid bilayer into more curved. And we have also confirmation from the small angle X-ray scattering, this from the unmodified system and this with low concentration. So we have here the space group from the cubic phase, and here we have also the space group from the cubic phase, but also the lamellar peaks, of course, for these samples with the highest concentration. So last time we also did the fast field cycling NMR. So I measured longitudinal relaxation rate for 5 samples, and you can see that this is completely flat. This is we can tell this is boring, but it's not, because it was very interesting for us that these extreme samples, so this with 10% and 50% of DTPA, these samples have the lowest relaxation rate, and that was really strange for us. That's why we measured the concentration of gadolinium in our system, and we used 2 methods. Of course, NMR, we we have mineralized samples, and we used also calibration curve to obtain gadolinium concentration. And we had a second method, which is ionic coupled plasma mass spectroscopy, to compare these results. And you can see that the difference between them is about 2 to 3%. So that's good. That means when you don't have ICP-MS in your lab, you can obtain your concentration by using NMR. But what was the most important? Theoretically, when we're increasing the amount of gadolinium in our samples, we can see from the results, ICP-MS here, that in fact the concentration is decreasing. So this is the opposite. It was not normal and not so obvious for us. Now we are working with the full NMRD profile with chosen samples, and we need to fit some models, some theoretical models to know better our system. So, but now we can say that at concentration above the optimal, the incorporation of gadolinium was limited. So likely these disturbances in the system structure, and this leads this T1 relaxation lengthening. So take-home messages. Our system form aqueous dispersion characterized by long-term stability up to 8 weeks, which is important for biomedical application. After dispersion, this system with low concentration of gadolinium retain their highly ordered structure, cubic and hexagonal one, and the system with the higher concentration of gadolinium yielded nanoparticles with disordered interiors. And all dispersion showed enhanced relaxivity to compared to this low molecular weight commercially used contrast agent. But the most important that our system showed great potential as T1 positive contrast agent. And this is our latest publication. So if you are curious, this is the QR code for our publication. And I wanted to thank every person from the team which I'm working with. And special thanks to my supervisor, Dr. Engineer Dorota Flack, and also Professor Michał Banaszak. Thank you for funding. And if I have a second, I want to encourage especially PhD students to participate in our Ampere NMR school organized by Adam Mickiewicz University, but mainly it is organized by Roxana Markiewicz. I think this is the great opportunity to meet new people in the NMR society, but also we have a broad topic, so you can learn everything from the NMR study. So that's some advertisement, sorry, but I think this is a great occasion for young people, and thank you for your attention.
Thank you very much, Karolina, for a talk. I fully support the advertisement for Ampere NMR School. It's a great event.
Thank you.
And we are open for the discussion. So if you want to ask questions, please turn on your microphone and if possible, camera. If your microphone is not working, you can write the question on the chat. So does anyone have any question?
I have a question, yes. if I may. So actually two short questions. So one, is transverse relaxation also affected? I mean, T2. And second question would be, do you imagine applications outside in vivo? Because these gadolinium agents are used to shorten T1 also in vitro samples, as far as I know. So do this particular contrast agents could be used in other applications?
So the first question, we did also T2 weighted images, but they were not good as T1 weighted images. That's why, because T1 is better for the paramagnetic system and gadolinium is a paramagnetic element, but T2 is better for the super paramagnetic system. That's why it's better to use this contrast agent based on gadolinium in the T1 weighted images. And the second question, you mean the in vivo test, but in the mouse or something different?
No, I mean, your contrast agents are designed to be biocompatible, right?
Yeah.
That's the point. But can you imagine applications outside in vivo? For example, either for imaging or for spectroscopy, where this particular kind of contrast agents would be useful? Or are they, or like the main purpose is to make them biocompatible? And yeah.
To be completely honest, I didn't think about it, but I think it's very good to consider that. So I will think about it. I will consider that. Thank you.
Okay, thank you.
We might have time for one very short question. So if anyone wants, this is the moment. If not, we'll switch now to the second presentation of today.
Thank you.
Thank you. So thank you very much, Karolina, for your talk.